We're now starting a totally different type of chemistry called organic chemistry. This organic chemistry is no longer quantitative, it's more qualitative, meaning that you're not dealing with numbers. But in organic chemistry, what we're actually going to be looking at is connectivity and structure, function, and a little bit of how reactions change molecules. As you read through Chapter 10, be sure to do the in-text problems. And when you get through with reading, do all the assigned problems at the end of the chapter. It's going to be the same as it is in the first part of the course, that you will not do well unless you do all the problems that have been assigned. You're going to find that this material is pretty confusing unless you do the problems. It is through the problems that you start to understand the material. So, I'm trying to motivate you. Get into those problems, do them, and when you don't get right answers, be sure to come for help. I'm there for you.
Organic chemistry is a chemistry of carbon, and carbon can bond to itself as many other atoms. And something unique about carbon is that it can make chains. It has a huge variety of what it can do. It can make single bonds to carbon, single bonds to hydrogen, single bonds to oxygen, sulfur, nitrogen, phosphorus. Carbon can make double bonds to itself and many others, type of nonmetals. It can make triple bonds. It even can make bonds to metal. It's an incredibly flexible type of chemistry, and as a result, the organic chemistry area is a tremendously huge area of chemistry. This actually is a chemistry that leads into biological chemistry. Now, the first thing we're going to have to do is go back to writing Lewis dot structures. I'm going to give you some simplified guidelines for writing Lewis dot structures so as to speed your ability to write down molecules. If you learn these guidelines, it will help you write correct structures, and correct structures is the only way to get through organic chemistry. In the structures that we're going to be looking at, carbon will have exactly 4 bonds. Now, carbon can have fewer bonds than that, but that would be when it's charged. So we're not going to be looking at charged carbons, so carbon will always have 4 bonds. That can be 4 single bonds, 2 single bonds and a double bond, 2 double bonds, or a triple bond and a single bond. But there almost always will be 4 bonds. If I look at oxygen, oxygen will have 2 bonds plus 2 non-bonding pairs. It can have a charge on it, and we will be looking at some that have charges on it. And when it has a negative charge, it only has a single bond to it. But we'll look at that later on. Now, oxygen is called a heteroatom. Any atom other than carbon and hydrogen in an organic molecule is called a heteroatom. Make sure every time that you write an oxygen down that it has 2 bonds and 2 non-bonding pairs. It can either be 2 single bonds or a double bond. Every hydrogen has 1 bond and only 1 bond. If you ever break that bond, the hydrogen comes off as a hydrogen ion, a proton, and it leaves a negative charge behind on the atom that it left. Halogens always have 1 bond and 3 non-bonds, and nitrogen always has 3 bonds plus a non-bonding pair. If you ever put 4 bonds on a nitrogen, then it has a positive charge. When nitrogen is neutral, the 3 bonds can either be 3 single bonds, a double bond and a single bond, or a triple bond. There are several different ways of writing structures or molecules. We can either write the molecular formula, which just tells us how many atoms that we have of each in that molecule. We can write an empirical formula, which is just a ratio of the elements. We can write a structural formula in which we actually show what atoms are bound to what atoms. And then we're going to learn how to draw condensed formulas, which is a type of shorthand that we use. And we will actually see that there are three-dimensional drawings that we do so as to show how the bonds orient in space. A molecular formula example is shown here with butane. You can see butane is just shown with 4 carbon atoms and 10 hydrogen atoms. It's telling you how many atoms of each element that we find in a molecule of butane. If I'm going to write the empirical formula, I would see that it is C2H5. The 4 to 10 can be simplified down to a 2 to 5 ratio, and so this is the empirical formula. The structural formula actually shows how the hydrogens are attached to the carbons and the carbons attached to each other. And this is going to be something that we use a lot. The condensed formula actually doesn't show all the bonds, but it's still telling you the connectivity, which we'll look at this a little bit more in depth later on. But the hydrogens are only attached to one atom, so they're only attached to the carbon. And this little condensed formula that we're showing here, it looks kind of confusing to you now, but as we go on, you're going to see it becomes less confusing as you get used to it. The three-dimensional gives you bond angles, and this isn't really truly three-dimensional because you're not showing how the angles are coming out of the page and going behind the page as they would if it was truly a three-dimensional drawing, but it's close to it. Now let's look at these condensed formulas. When we're writing condensed formulas, we're actually writing groups of the parts of the molecule. And it's assuming that you understand how bonding occurs, and that you know that the hydrogen is only bonding to the atom that it follows, usually. Sometimes we write it a little bit different, but usually it's the atom that it's following that it's bound to. And down here for butane, I'm actually showing how these groups can be translated from a structural formula down to this condensed formula. You can see that this carbon with 3 hydrogens attached can be written as CH3, and then attached to a CH2, and then attached to a CH2, and then attached to a CH3. This all is written smashed together at the bottom, which is what we call our condensed form. In these condensed structures, the atoms are all drawn in, and the bonds are omitted. Single bonds are omitted, double bonds are written in, and lone pairs are usually omitted. So in a structural formula, we usually show the lone pairs because it's truly a Lewis dot structure. But when we go to write our condensed structures, we leave them out. These condensed formulas are telling you the connectivity. Because hydrogen is bound to the atom that it follows, we know then that the atoms other than hydrogen are connected to each other in a row. So if we look at this molecule here, that has 2 carbons in it and 6 hydrogens, you can know that the 3 hydrogens are attached to the first carbon, then that carbon must be attached to the next carbon, and then those 3 hydrogens are attached to it. So write a structural formula for that molecule and for the one below, trying to apply those principles that we're just learning right now. Okay, the structural formula for this compound should be where the 2 carbons are attached to each other because they're following each other, and the hydrogens are then attached all around to the carbon. If I look at the next molecule, I'll see that the carbons are attached to each other, and notice the double bond is between the first 2, and then there's a double bond between the carbon and the oxygen. and you can then know that the two hydrogens that are on the first carbon are attached to it. The hydrogen that comes after the second carbon is attached to it, and the hydrogen that comes after the third carbon is attached to it. You also may have drawn in two non-bonding pairs on the oxygen, which I have neglected to draw in this picture. Parentheses can be used, and sometimes these can get confusing, but I hope that after you see a number of examples, you'll start to get the idea of how they're used. If we write it so that there are two carbon plus two hydrogen groups, we call that a methylene group. If there are two methylene groups, we can put parentheses around a methylene and then write a subscript 2. This means that they are following each other in the chain. And so if you look at this formula on the left with the parentheses in it, it can be rewritten as a formula on the right, where the carbon hydrogens, the methylene groups, are actually following each other in the chain. Another example of how we use parentheses is in the bottom structure, and you can see there is a CH3 inside the parentheses. We call that a methyl group. There are two of them in the parentheses. Now, they cannot follow each other because that would put 5 bonds on one carbon. So they must both be attached to that carbon that comes after the subscript 2. And that only helps to make sense because that carbon has only a hydrogen and the last carbon in the structure attached to it, so it needs to have two other groups attached to it. So we rewrite that structure as it is written as on the right. We have something called isomers. An isomer is a compound with the same formula but with different connectivity. This is called a structural isomer. If we look at this example below, you can see that the compound on the left has 1 carbon, 1 nitrogen, 1 oxygen, and 3 hydrogens. If I look at the compound on the right, it has 1 carbon, 1 nitrogen, 1 oxygen, and 3 hydrogens. They have the same number of atoms of each element, but they're put together differently. They have different connectivity. That is what a structural isomer is.